Why is the SR-71 Blackbird considered the most unsurpassed supersonic reconnaissance aircraft in the world? On May 1, 1960, in the Soviet Union, over Sverdlovsk, a Soviet anti-aircraft missile hit an American U-2 high-altitude reconnaissance aircraft piloted by Francis Gary Powers. This incident became one of the most notorious scandals of the Cold War, but for the engineers of the secret division of Skunk Works, it became the starting point for creating the most incredible aircraft in the history of aviation. Since an airplane can be shot down at an altitude of 20 kilometers, it means that you need to fly even higher and so fast that not a single missile can catch up with it. This is how the project was born, which eventually turned into the SR-71 Blackbird, a car that became a symbol of engineering madness and engineering genius at the same time. Clarence Kelly Johnson, the legendary Lockheed designer, took on a task that many considered impossible. The first stage was the A-12, a single-seat reconnaissance aircraft developed for the CIA as part of the Oxcart project. But the Air Force wanted more, a two-seat vehicle with an expanded range of reconnaissance equipment capable of operating at an even greater range. This is how the SR-71 appeared, inheriting the revolutionary aerodynamic design from the A-12, but becoming larger, heavier, and even more advanced. The first flight took place on December 22, 1964, and the aircraft began to arrive in the United States Air Force in 1966. From that moment until the decommissioning in 1998, not a single SR-71 was shot down by the enemy, not once in 32 years of operation. To understand the scale of the engineering challenge, it is enough to know the speed, more than 3 Mach. At a cruising speed of about 3,300 kilometers per hour, the aircraft was moving faster than a bullet from some types of small arms. At this speed, the air ceases to be just a medium, it turns into an aggressive opponent. Friction with the atmosphere warmed the leading edge of the wing to 400 degrees Celsius, and the average temperature of the skin in a cruising flight was about 260 degrees. Aluminum, which was used to build conventional aircraft, lost its strength and deformed at such temperatures. The only solution was titanium, a metal that is light, heat-resistant, and incredibly difficult to process. The United States did not have sufficient titanium reserves for mass production. The world's largest supplier of titanium ore was the Soviet Union, the very country for exploration over whose territory Blackbird was created. The CIA organized a network of shell companies around the world through which titanium was purchased from Soviet enterprises and supplied to Lockheed plants in Burbank, California. Moscow unknowingly supplied America with the material to build an airplane designed to spy on it. Working with titanium required a complete revision of production technologies. Conventional cadmium tools left traces of corrosion on titanium, so the entire tool had to be replaced. The tap water used to wash the parts contained chlorine, which corroded titanium alloys, and it was replaced with distilled water. Even the marking pencils had to be replaced. The trace of irregular lead caused local corrosion when heated. Every bolt, every rivet, every fastener element was designed from scratch. The serial parts were not suitable for a machine operating in conditions close to space. The fuel system deserves special mention. Ordinary aviation kerosene at 3 Mach would turn into a bomb. When the fuselage was heated, the standard fuel would simply ignite from contact with the red-hot walls of the tanks. Special JP-7 fuel was developed for the SR-71, which was so stable that it could not be ignited with a match or even a torch.
Triethylborane, a substance that self-ignites upon contact with air, was used to ignite JP-7 in the combustion chamber. Each refueling cost hundreds of thousands of dollars, and that's without taking into account the cost of specialized KC-135Q tankers, which were the only aircraft capable of delivering JP-7s in the air. The aircraft's design was equally unusual. The tailless scheme with a thin, triangular wing, the sweep of the leading edge of which was 60 degrees, provided minimal resistance at supersonic speeds. Two all-rotating keels mounted on the engine nacelles and tilted inwards by 15 degrees served as a vertical tail. There was no horizontal stabilizer at all. The dark blue, almost black color, which gave the aircraft the nickname Blackbird, served not only for camouflage against the background of the night sky, it helped to radiate heat accumulated by the skin in flight, reducing the thermal load on the structure. The SR-71 power plant deserves a separate book. The Pratt & Whitney J58 engines were in fact a hybrid of a turbojet and a ramjet engine. At subsonic speeds, they worked like conventional turbojet engines, but as they accelerated, more and more of the air was redirected directly into the afterburner, bypassing the compressor, and at Mach 3, the engine actually turned into a ramjet. Air intakes with movable cones regulated the airflow, slowing it from supersonic speed to subsonic before entering the compressor, and at the same time provided up to 80% of thrust by compressing the air in the air intake itself. If the cone shifted even for a fraction of a second incorrectly, there was a non-start, an instantaneous loss of thrust on one engine, which could throw the aircraft into an uncontrolled roll. The crew of 2 people, a pilot and an intelligence officer, worked in conditions close to space conditions. At the working altitude of more than 25 kilometers, the atmospheric pressure is so low that without a spacesuit, a person's blood boils. For the SR-71, David Clark developed altitude-compensating full-pressure suits, which were subsequently used by the crews of the Space Shuttle. Before each flight, the pilots underwent a training procedure comparable to the pre-flight training of astronauts, including breathing pure oxygen to remove nitrogen from the blood and prevent Cessna disease. In total, 32 copies of the SR-71 were built, including serial SR-71A reconnaissance aircraft and SR-71B training aircraft. 12 of them were lost in accidents and catastrophes, none due to enemy actions, all due to technical failures or crew errors. This shows how extreme the operation of these machines was. Each flight represented a balancing act on the edge of the possible. The slightest malfunction in the cooling system, navigation, or air intake control could lead to the loss of the aircraft. The cost of the program was astounding, even by the standards of the Pentagon. One plane cost $30 to $40 million in the prices of the 60s and 70s, which in terms of modern money amounts to hundreds of millions. But the cost of the aircraft itself was just the tip of the iceberg. Every hour of flight required dozens of hours of maintenance. Preparing for a single flight was comparable in complexity and cost to preparing for a space launch. The support infrastructure, special climate-controlled hangars, tankers, ground tracking stations, and intelligence processing cost no less than the planes themselves. Over the years, the SR-71 has carried out reconnaissance missions over Vietnam, North Korea, the Middle East, and many other hotspots. The missile evasion tactics were simple. Instead of evasive maneuvers, the pilot simply gave full throttle and gained altitude. At speeds in excess of 3 Mach and an altitude of more than 25 kilometers, the aircraft was beyond the reach of the vast majority of anti-aircraft missiles of that time.
During all the years of service, more than 4,000 missiles were fired at the SR-71. Not a single one hit the target. In 1998, the SR-71 was finally withdrawn from the U.S. Air Force. There were several reasons: the enormous cost of operation, the emergence of reconnaissance satellites capable of taking images of comparable quality without risks to the crew, and the development of unmanned aerial vehicles. 2 aircraft continued to fly at NASA until 1999 as part of research programs. Today, the surviving Blackbirds are in aviation museums across America, and several D-21 vehicles and unmanned drones are preserved at the Armstrong Flight Research Center. As of 2025, the SR-71 remains the fastest manned production aircraft in the world, a record that has not been broken in more than half a century. Still, one mystery remains unsolved. What is the SR-71's true top speed? The official record, set in 1976, is 3,529.6 kilometers per hour, but the pilots who flew the Blackbird have repeatedly mentioned in memoirs and interviews that the instruments sometimes showed values significantly higher than this figure. The reason why the true speed limit has never been set lies in the very nature of the car. The SR-71 never accelerated to its design limit intentionally. Each additional Mach meant an exponential increase in the temperature of the skin, and exceeding a certain threshold threatened to destroy the structure. In addition, at extreme speeds, the engines operated in modes that were not fully understood even by Pratt & Whitney engineers. No commander in his right mind would risk a crew and an aircraft worth tens of millions of dollars for an entry in the Book of Records. Secrecy played a role too. Even if individual crews accidentally or intentionally exceeded official limits, this data was classified and not subject to disclosure. Part of the program's documentation is still classified. Finally, the very concept of maximum speed for the SR-71 did not have a clear definition. The theoretical ceiling depended on the outside temperature, flight altitude, fuel mass, and the condition of a particular instance. Each aircraft was unique to a certain extent due to manual assembly and individual tolerances. Friends, what do you think about this?